Hello and welcome. This is the annual update for the Linux Feature Working Group. Oops, my bad. At least once per year, I have to pronounce it in full name. So let me restart. Hello and welcome. This is the annual update for the Linux Feature for Safety Critical System Working Group. And as you may have guessed, in this presentation, I'll give you an overview of what the working group has accomplished over the past year. So, a word about the host. I don't want to annoy this audience with my biography, but since I've taken over the working group after Elana, and some of you may not know me, I should at least introduce myself. I am Alessandro, the guy in the photo, and I am a Linux developer at Red Hat working in the automotive distribution. My journey in the world of functional safety started with my automotive tasks, but I come from a strong background in security and Linux in general. And yes, while security and safety are different beasts, one deals with intentional attack and the other deals with accidental fault, understanding the inner working of corruption definitely help when thinking about safety. I've been involved with the ELISA project since 2021, contributing at various levels in the tools and architecture working group. And as you probably have guessed by now, I'm currently chairing this Linux Feature working group. So, a slide about the working group statement is something which is expected in this kind of presentation, right? So the mission of this working group sounds simple. Explore the Linux feature that could benefit safety critical system and create a community where developers and system producers work together. Easy, right? We'll see. First off, investigation isn't just about spotting features that already exist. It's about digging deeper, understand their limitations, see how they perform in real-world environment, and figuring out where we need to fix things up. The mission statement talks about contributing by patch to the kernel code, which is great, but we are not quite at patch party level just yet. Then there is the collaboration with other working group, which is also look like a breeze on the paper, but let's be honest, it's more than just talking. We need to define concrete use case, test feature in real or simulated system, and actually share our findings. That's how we build knowledge that benefits everyone. Finally, our aim is to help Linux kernel to evolve in a way that meets safety critical needs, whether it's through configuration, best practice, or rolling up our sleep and working on those kernel patch I was mentioning. That's what this statement says, so let's see what we've done so far. Oops. Here's the achievements slide for this year. Let's have an overview. We began with a significant restart phase, which, to be honest, took a fair bit of time. During this phase, I worked closely with community to regain and realign priorities and set clear direction for the next step. Think of it as the foundation before we could get the fun stuff. And once we had that direction, we focused on two major challenges. The first was define a minimal kernel configuration. We explore various alternatives. After some discussion, we decided that we would need our target platform. We quickly realized that without a specific target in mind, configuration decision would be like shooting in the dark. This effort was also discussed in the architecture working group meeting, which eventually led to our second challenge. As second challenge, ongoing challenge to be fair, is identify the minimal set of features required by any Linux application. While this work is still in progress, we made already significant progress. We defined the problem, set up a methodology, and already have some initial investigation result. Let's see the milestone in details. As for a word on the minimal kernel configuration, let me explain why focusing on it is essential for safety critical system. The first key principle is for safety is that less is better. Reducing the number of enabled features in the kernel lowers the system complexity, which in turn reduces the potential of failures. Think like a machinery. Fewer moving parts are less likely to break. For this reason, a streamlined kernel can improve reliability and safety in general. But safety requirements aren't the same across all fields. Automotive, aerospace, healthcare, for example, have diverse needs. That makes it important to establish a common baseline, a kernel configuration that provides essential features without adding unnecessary complexity. Now, when it comes to define a minimal kernel configuration, there is a key challenge. You can't configure the kernel without knowing which is your target. Different hardware architecture come with different requirements and essential features. So we need to carefully choose a target that would provide a balance between relevance and flexibility. We explore various alternatives, considering factors like availability, ease of testing, and applicability to safety critical environment. After this investigation, we decided that AR64 on QEMU was our target architecture. This choice provides a controlled environment for testing and validating kernel configuration while being widely accessible for the community. An important factor in this decision was also that the QEMU model using BIRT.io as proposal for silicon implementation. This means that the insight gained during working on QEMU may have a direct impact on real-world hardware development, making it a strategic and forward-looking choice for our work. The next milestone is the Linux minimal feature investigation. This investigation was initiated in response to a discussion in the architecture working group. The group raised an important question. What is the bare minimum Linux feature must provide to even a trivial program like a simple infinite loop program? And please note that feature typically maps into subsystem. In any case, answering this question is crucial, and it helps to define baseline for Linux configuration that can be useful across the various safety critical applications. By stripping the kernel down to its core essential, we reduce the complexity and improve predictability, both for which are fundamental for safety critical system. The expected result for this investigation is to identify this essential feature, which then can guide to the definition of minimal, well-documented configuration. This would provide a common starting point for different industries and use cases. So, to conduct this investigation, we first explored various methods for realizing the kernel behavior. One option was to manually review and trace the kernel subsystem code, attempting to infer which components are essential. However, given the complexity and the size of the kernel code base, this approach proved to be impractical. Another option on the table was to use QEMU as a debugger and trace the system by that. Although this method would require to add no code to the kernel, the GDB infrastructure typically used to fetch information isn't well suited for this task. Significant code production would have been required to make this approach feasible. Instead, we choose to use a dynamic tracing methodology using the Linux ftrace subsystem. About the investigation, we developed a simple C application that performs a basic operation and then enters in an infinite loop. This program was carefully crafted to avoid introducing any unnecessary operation, ensuring that we capture only fundamental kernel interaction. And another critical component for this architecture or methodology, if you will, was the launcher program, a lightweight application designed to prepare the tracing subsystem and the environment to minimizing the operating system interference. This is crucial because tracing a live application on Linux can be disrupted by OS activities, such interrupts. As said, the investigation has already yielded some result. We identified essential kernel mechanisms required to support even the simplest user application, offering a valuable insight for defining a minimal kernel configuration. One notable observation is the role of the randomization. Security systems often rely on randomization to make attacks harder, while safety-critical systems prioritize predictability. Balancing of these different needs is crucial. The randomization discussion has prompted a valuable input from the Aereo working group. They highlight the importance of clear configuration guidance and emphasize that system requirements should be driven by functional hazard assessment. In other words, if randomization isn't explicitly required, it should be excluded to maintain simplicity and predictability of the software. A few more interactions between minimal config quest and the minimal feature probing is needed to reach stable result. And as soon as we reach this, a new document with feature list will be published. And so we reach the next step. So what are we planning to do next? Once we complete the minimal feature list, the next logical step is dig into the feature we already have, the one that we found by the investigation. Take, for example, memory allocation. From an application standpoint, it seems simple enough, just allocate memory. But let's face it, sometimes as basic as memory allocation can quickly spiral into a beastly complex task. Allocating memory in the kernel could range from a relatively simple scan a free blocks list and return one, to the full-blown swap the user memory to disk and return a freed block. And don't forget about input from other working group, that we got a solid track record of collaboration with tools and architecture team. And sometimes this discussion lead to a new work stream. Last but not least, our original agenda, we set just after the restart, was designed to tackle fundamental operations like memory management and boot process that we definitely need to look at. So, as you said, there's no shortage of topics to explore. So let me slip a little commercial here. Working group would love to have anyone who wants to get involved. And that is all that I get. Any question?
Thank you so much, Alessandro. There is actually one question already in the chat. And it says, what is the target platform for minimal kernel configuration work?
Well, we decide. Yeah, we decide during the configuration quest, the minimal configuration quest, that having this analysis without a target platform is quite not possible. So we decide QEMU and AR64 for that and all other activities that the working group is doing. So for the moment, our target, our platform is AR64 on QEMU hardware. It allows everyone to experiment, since it did not bind to hardware, and it is quite actual and easy to use to get anyone involved without any pain.
Thanks. Do we have further questions? Everybody's also free to raise their hand, and then Min can unmute you. If there's anyone who would like to ask something. Nothing more in the chat. Nobody raising their hand. Then I will say thanks, Alessandro.
Thank you.